In the world of railways, there are three main methods of powering locomotives: steam, diesel, and electricity. Naturally, engineers experimented and combined some of these locomotive types in attempts to produce better and more efficient machines, resulting in semi-successful steam-diesel hybrid locomotives and the current most popular locomotive type, diesel-electric. That leaves us then with the question, what does a steam-electric hybrid look like? The answer is something like this. By the late 1800s, steam was the dominant means of locomotive power on pretty much every railway around the world. However, electricity was slowly becoming more refined, and as such, many railway companies saw the benefits of electrification as something worth pursuing. Electric locomotives could accelerate better and reach higher top speeds than contemporary steam engines, but required a lot of costly infrastructure in order to run. Another advantage electric locomotives had over steam was they didn't produce hammer blow, a force produced by the engine's cylinders that caused the driving wheels to effectively hammer the rails and locomotive, causing damage, especially when travelling at higher speeds. Wanting to try and alleviate the effects of hammer blow, Jean-Jacques Heilmann decided to experiment by giving steam locomotives electric transmission. This having the added benefit of giving the locomotive the same high-speed performance as an electric locomotive while not requiring any of the expensive infrastructure. After settling on using DC motors and generators, Heilmann built a prototype engine with a triple expansion steam engine, a generator capable of providing 360 kilowatts and a tender. The locomotive worked by using steam to generate electricity, which would then directly power the electric motors connected to the locomotive's wheels. Seemingly pleased with the results, he patented the design in 1890 and founded his own company, the Société Industrielle des Moteurs Électriques et Vapeur, intent on building a proper prototype locomotive. Construction of his new project began in 1892, and by 1893 this unique locomotive was complete. Coming in at 16.5 meters long and weighing 100 tons, the engine featured a boiler from French Shipbuilding Company, the New Society of Forges and Shipyard of the Mediterranean, the frames came from the French Railway Equipment Company, the engine came from the Swiss Locomotive and Machine Works, and the electrical equipment came from Braun Bavarian C in Switzerland. The cab was positioned at the front of the engine, with the smoke box and funnel positioned at the rear, making it appear as if it was driving backwards. Water was stored in side tanks and the coal in bunkers at either side of the firebox. The engine was equipped with two cylinders, one high pressure and one low pressure, and would directly power the dynamo. Rated at approximately 500 kilowatts, the dynamo powered the 8 traction motors used to drive the locomotive, with each axle having its own motor. The motors were connected in parallel, and at low speeds the motors could be halved to 2 sets of 4. There was also another, less powerful dynamo which generated electricity for carriage lighting. As well as air brakes, the locomotive was also fitted with disc brakes too, something quite unusual for a railway locomotive of the time. The end result scarcely looked like a steam locomotive at all, and functionally is more comparable to a modern diesel-electric locomotive. Because of its unusual transmission, Heilmann decided to name his engine La Fusée Électrique, this being French for the electric rocket, as a nod to Stephenson's rocket. Testing began in 1894, with Fusée tackling the tricky line from Buzeville-la-Grenière to Le Havre, a route containing a 10-kilometer climb with grades averaging 1 in 125. An average speed of 51.5 kilometers an hour was achieved on the first run, with consecutive trips progressively getting faster. By the fourth trip, Fusée was averaging 59.4 kilometers an hour, achieving 70 kilometers an hour on level rails. A top speed of 107 kilometers an hour was achieved in a later test, and as a result the locomotive was used to pull a regular service to Paris. It wasn't just the engine's speed that was impressive either. It was said to ride as smoothly as a Pullman carriage and used 15% less coal than a conventional locomotive. As such, once the trials were over, the Chemin de Fer de l'Ouest put in an order for 2 of Heilmann's engines to test on their line. Fusée was broken up in 1897, but in its place came numbers 8001 and 8002. These were essentially the same design as their predecessor, but bigger, measuring in at 28.3 meters, the Lentz firebox was swapped out for Belpaire, and the dynamos and engine blocks were replaced with much beefier units. Unlike the prototype, these two were fitted with reversing mechanisms, allowing them to work comfortably in either direction. The first test run was conducted in November 1897 with great success, but with the engine's speed limited to 30 km an hour. The speed restriction was removed for later tests, and the Heilmanns didn't disappoint. One of the engines managed to clock a speed of 100 km an hour while pulling a 250-ton passenger train, with one of them managing to reach 120 km an hour on a later trial. What gave these engines such incredible performance was not only their electric transmission, but also the fact that the weight of the boiler and dynamos rested perfectly on the bogies, greatly improving the locomotive's adhesion. This, combined with their fuel efficiency and smooth quiet running, made them very popular, with railways in Russia, Germany and the US showing interest. However, they still came with drawbacks. Firstly was their weight. As much as the engine and dynamos helped with adhesion, they also added a few extra tons to the locomotive's overall weight, making them much heavier on their wheels than contemporary steam locomotives of a similar size. The extra weight didn't seem to improve their power much either, as from what I've gathered, despite their impressive starting traction, their overall power wasn't as great as that of contemporary steam engines, which leads on to another drawback: unnecessary conversion of energy. In a conventional steam locomotive, the power produced by the boiler is immediately transferred to the cylinders, which then power the engine's wheels. Because of this, most of the locomotive's energy goes directly to the wheels with little being lost. Heilmann's design, however, required the energy from the boiler be converted to electrical energy first before being sent to the motors, where it's then converted back into kinetic energy, resulting in some of that initial power being lost in the conversion process. But the biggest drawback the Heilmanns had was that, for the time, they were too complex to operate and maintain. Operating the engine required a driver, fireman, and an electrician pilot to maintain the electrical components, which meant paying more crew to operate one locomotive. The layout of the engine as well also meant that there was a great big dynamo in between the driver and fireman, making communication between the two significantly more difficult. Because electrical locomotives were still an emerging technology, parts were expensive, and by extension, so was fitting them. Not to mention, you had to essentially maintain a mini power plant on top of the workings of a regular locomotive. Don't get me wrong, the performance and fuel economy for the time was phenomenal, granting railways many of the benefits of electric operations without the need for the infrastructure. But the simple fact that they cost more for less power compared to a standard steam engine was enough of a drawback for railways to lose interest. With enthusiasm for the design, both local and foreign, drying up, Heilmann sold his business in 1898 to Westinghouse and moved on to designing hybrid cars instead. 8001 and 8002 were retired and scrapped not long afterwards. Though all of the engines were scrapped, one Heilmann locomotive technically survives in the form of a 10th scale model of the prototype built by Heilmann himself in 1903, currently on display at the National Conservatory of Arts and Crafts in Paris. Given that most of the criticisms Heilmann's engines faced were later used to criticize diesel-electric engines, it's fair to say he may have been a little ahead of his time with the design. Might the engines have proved to be more popular if they were built at a later time when such electrical equipment was more common? It's not likely, but who can know for sure? All we do know is that they're another example of an invention being a little too ahead of their time. A key part of what makes trains so efficient are their wheels. Only a small part of an engine's wheel touches the rail at any given time, and combined with the fact that steel on steel is very slippery, you end up with very little friction, making it easy to move heavy loads at high speeds. This lack of friction, however, can also be an issue, as less surface area on the rails means less traction, making it difficult to start moving heavier loads and climb hills. Many designers and engineers wanted to find ways of increasing an engine's traction to improve performance without sacrificing the efficiency of steel on steel, one of them being C.E. Swinnerton of the Swinnerton Locomotive Driving Wheel Company. His idea was to create a wheel that wasn't round, but polygonal, the idea being that because each side of the shape was flat, it would provide more contact between wheel and rail than a circular one, and thus more traction. Confident in the idea, Swinnerton's company ordered a 422 locomotive from the Hinkley Locomotive Works of Boston in 1887, fitted with a set of 5-foot 6-inch polygonal wheels. Most modern sources say that each wheel had 118 sides, each about 2 inches long, while an issue of Scientific American from 1890 states that the wheels had 210 sides, each 1 inch in length. Regardless, they spared no expense as the engine was also fitted with Westinghouse automatic and vacuum brakes, a water scoop, and steam heating equipment for passenger carriages. A pneumatic cylinder and lever was also fitted to the driving wheels, which would allow the footplate crew to increase the amount of weight placed upon them to further increase tractive effort. Named Onward, it was put to work hauling coal trains between Boston and Lowell, before moving to the Boston and Maine Railroad where it pulled the Portland Express. By this point, several other engines had been fitted with Swinnerton's polygonal wheels to test the design, but Onward was built specifically to test the design to its limit. In 1889, a series of tests were conducted to see how many cars Onward could pull up a gradient of 1 in 60 with a standard set of wheels, before swapping them out for the polygonal ones. The results claimed that Onward's performance was notably better with the polygonal tyres than the standard ones. Examiners also noted how the engine ran just as smoothly as one with standard wheels, and not bumpy like one would expect. So, if these wheels could improve performance and not interfere with locomotive operations, then why did they never take off? Well, the simplest answer is cost and maintenance. The tyres on many steam locomotives required frequent servicing and replacement as a result of wear and tear, but could be easily turned on a lathe to correct any issues. Polygonal wheels, meanwhile, would require a significant amount more time to service in comparison, and might even need replacing more often as the edges of the shape would eventually wear down into a circle if unmaintained for too long. The Swinnerton Locomotive Driving Wheel Company seemed to claim the wheels could be milled cheaply and easily, but this was an extra step in what was already a lengthy process. Additionally, braking would be much more difficult, as brake blocks on normal locomotives are curved to fit snugly onto the wheel to grip as much of it as possible. With a polygonal shape, the surface of the wheel is uneven, making it harder to grip, and would grind against the brake block more than be gripped by it, wearing out both the wheel and brake much faster. And finally, while the wheels did improve the engine's performance, it wasn't by enough for railroads to consider them viable. Something Swinnerton hadn't taken into account was how much steel deformed under the weight of a standard wheel, providing a greater contact area than they first thought. What likely didn't help was Onward itself. Both single drivers and American-style engines were long out of date when it was built. Most railroads likely saw Onward as an improved version of an outdated design and didn't think much more of it, despite it proving to be nearly as powerful as a standard 440. In the end, Swinnerton tried selling the design for use on streetcars, but got nowhere. Though it's worth noting the cast iron wheels produced by the Lobdell Wheel Company were made with treads similar to Swinnerton's design. Onward itself was eventually sold to the Portland and Rochester Railroad after being fitted with a standard set of wheels. It was later sent to the Manchester Locomotive Works and converted into a 440 before finally being retired and scrapped in 1905. Swinnerton's polygonal wheels then are a fascinating story. While they genuinely seem to increase the performance of locomotives, the interest simply wasn't there to make them a success. Put it down to them being unconventional, awkward to maintain, or just something railroads didn't understand. It just goes to show that, at the end of the day, onwards doesn't necessarily mean upwards. By the 1980s, steam power had become redundant on many railways across the world, with most running diesel engines or fully electrifying their lines. Some engineers, however, still felt that steam was a viable option, and tried their best to prove that steam power could keep up with the times. In South Africa, this resulted in an engineer trying to beat out diesel power with a little help from a devil. Built in 1953, the Class 25s of South African railways were hard-working beasts, and for their time quite intricate in design, being some of the most modern steam locomotives in the world, fitted with condensing equipment to help them save water. They weren't without their faults, however, having a long history of needing to be modified and various features be replaced to keep them in working order. By 1973, the condensing equipment was considered too awkward and expensive to maintain, along with several other aspects of the engine's design, so it was decided they'd be rebuilt in order to make them cheaper and easier to run. At the time, South African railways wanted to transition from steam to diesel and electric engines. However, David Wardale, who was employed as a mechanical engineer on the railway, disagreed. He felt that steam power could still be drastically improved, and that because South Africa had such a plentiful supply of coal, it made more sense to use steam over diesel engines, with the price and availability of imported oil fluctuating. The railway held little interest in Wardale's ambition, but permitted him to trial his ideas when he promised they'd help reduce line-side fires. Wardale chose a Class 19D engine, number 2644, which was a notoriously bad performer, and had it fitted with better cylinders, better blast pipes, some other minor upgrades, and his secret weapon, a gas production combustion system, or GPCS for short. The way a traditional locomotive firebox works is coal is spread over a large grate. Once lit, the heat from the fire draws air up through the grate and into the firebox, helping the coal burn. A flammable gas is released from the burning coal, and opening the firebox door allows more air into the firebox to help this gas combust. The heat and burning gases are then drawn through the boiler tubes to heat the boiler before being exhausted out the smoke box. The problem with this system is the rapid rate at which air is drawn through the firebox often resulted in smaller, unburned pieces of coal getting pulled through the boiler and exhausted out the chimney. This not only meant that the engine was essentially wasting unburnt fuel, but the small particles moving at such a high speed effectively sandblasted many internal parts of the engine, causing a significant amount of wear on components. Not to mention that firemen had to maintain a thin bed of coals at all times when firing an engine. But too thin wouldn't produce enough heat, while too thick would stress parts of the firebox from the heat. As it was the gases that were released from the coal that produced most of the heat an engine needed, the gas producer combustion system worked by prioritizing releasing the gases from the coal and combusting it afterwards. The firebox grates had much smaller air holes to limit the amount of oxygen that got to the fire, and a nozzle would spray a small amount of exhaust steam from the cylinders up into the bed of coal. The coals were laid thicker, burned at a lower temperature, and the water combined with the slower airflow ensured that little to no unburned coal would be drawn through the boiler. Above the layer of coal were vents that allowed fast-moving air to enter the firebox and allow the released gases to combust. The hot gases would then flow through the boiler and then be exhausted as normal. This was a much more efficient way of burning coal, as not only did it ensure little to no fuel was left unburned, but the airflow ensured that no coal particles were flowing through the boiler and damaging components, or that any hot coals were being spat out causing line-side fires. An added bonus was that this layout also helped reduce the amount of clinker that built up at the bottom of the firebox. Once overhauled and after a few weeks of tuning, the modified 19D was found to not only be more powerful than its unmodified counterparts, but consume between 20 to 25% less fuel on average too. Footplate crews ended up nicknaming the engine Spooky, due to its unearthly performance and its quieter than usual exhaust. Deeming the experiment a success, South African Railways allowed Wardale to continue with his plan and modify one of the previously mentioned Class 25s, feeling that if he can modernise what was already seen as a modern steam locomotive design, then the railway might also see the same untapped potential in steam as he did. Engine number 3450 was selected and taken to the Salt River Workshops in Cape Town in 1979, where Wardale spent the next 2 years refitting it, not only with a GPCS, but many other minor alterations, including but not limited to a self-cleaning smoke box, better superheating, better cylinders, and a new feed water heater. The Vollschwarz valve gear itself was improved using measurements calculated on a computer. That's how up to date the engine was. On the 5th of February 1981, the engine was steamed for the first time, and after dealing with some leaks, the engine went for its first test run the next day. 3 days later, on the 9th, the engine was unveiled to the public, being given a bright red coat of paint and named LD Porter, after an Argentinian locomotive engineer who inspired many of the changes Wardale had made to the engine. The local press took a great interest in the locomotive, and by the end of the week, newspapers printing pictures of the engine had dubbed it the Red Devil. Its paint job, however, wasn't the only thing that earned it its nickname. Like the modified 19D before it, 3450 was found to be very fuel efficient, with savings of 28% on coal and 30% on water usage. Not only that, but the engine's overall pulling power was significantly stronger too. During tests, it was found that the dynamometer car used to measure the engine's power was faulty, and so most estimates of the engine's power were very conservative. Despite the skeptical measurements, the engine showed a 43% increase in drawbar horsepower at minimum, so it's possible that the engine was much more powerful than it was measured to be, while already being significantly more powerful than the rest of the Class 25s. As a result, the engine was officially reclassified into a Class 26, being the only locomotive of its class. All of this, paired with its size, really puts into perspective how absurd this engine was. The locomotive itself weighed 117 long tons, including the tender was over 90 foot in length, and had a starting tractive effort of 52,000 pound-feet. To put that into perspective, it was longer, heavier, and more powerful than a Gresley Pacific, while running on narrow-gauge 3-foot 6-inch rails. I think you'll agree that, on top of being an absolute unit, the name Red Devil was certainly earned. So much so that a nameplate reading Red Devil was fitted to its smoke deflectors, making the name official. There was, however, a devil in the engine's details too. Many footplate crews found the engine awkward to fire, with the locomotive's performance often depending on the quality of coal available. The lack of air holes also caused problems with ash building up on the firebox grate. A leaky superheater and temperamental boiler pump didn't do it any favours either, but its biggest drawback was its lack of traction. The Class 25s often suffered from wheel slip, especially when starting on or climbing grades, and Red Devil was no different. Even with better sanding gear, it just couldn't seem to overcome its problem with adhesion, essentially rendering all that extra power it had useless if it couldn't deploy it in any meaningful way. But in the end, it wasn't any of these little foibles that ended up condemning the project, but simply South African Railways' indifference to the engine altogether. The directors by this point had made up their minds, and wanted to make the switch to diesel engines, no matter how efficient steam power was by comparison. Wardale left South African Railways in 1984 once he realised the railway was steadfast on scrapping steam power, and moved on to other projects. Red Devil ended up being modified and partially converted back into a standard Class 25 to help resolve some of its issues. It was later withdrawn from service, but saved from scrap by a group of preservationists, who used it to pull special excursions until 2004, when it was eventually put into storage. It was recently restored into working order in 2018 and has since been carrying excursion trains during the South African winter. While certainly not the last great hurrah of steam power, the fact that Wardale was able to improve the performance of an engine so much just goes to show that steam locomotives might still have more to give than we first thought. Just be sure to practice your fiddle playing before you go about building another engine. You know, just in case. In the early days of steam, there were two important things to remember when it came to locomotive design. Bigger boilers meant more power, and bigger driving wheels meant more speed. The issue is, the bigger you make one, the less space you have for the other, as the boiler would often be mounted above the driving wheels, and so a balance had to be struck between the two. Logically then, if the size of one restricted the size of the other, then why not mount them separately? Then you could have a big powerful boiler and big fast driving wheels. Well, some engineers decided to give that a go, with unfavourable results. During his time at the Great Western, Isambard Kingdom Brunel had big ideas about the future of the railway, envisioning high-speed express services sprinting along the line. As the GWR didn't have their own locomotive works yet, in 1836 the company ordered express engines from various railway works across the country, with Brunel providing the following specifications. 1. While moving at 30 miles an hour, the piston must not travel at a rate exceeding 280 feet a minute. 2. The boiler pressure should be 50 psi. And 3. The weight of the engine must not exceed 10.5 tons. These specifications, however, were very restrictive. Not only were more powerful boilers available, but pistons could travel at a much faster rate without issue, and the railway's infrastructure was capable of supporting much heavier machines. As a result, the railway ended up with a vast array of underpowered 222 engines, which had massive driving wheels to keep piston travel low and small boilers to keep the weight down. With the smaller boilers severely stunting the performance of the other engines, R&W Hawthorne and Company thought that rather than sacrifice the boiler size to save on weight, they would instead mount the boiler on a separate carriage. This way they could have bigger wheels to keep the piston travel low and a bigger boiler to keep up with their demand. And because the driving wheels and boiler were on separate frames, the weight was spread out, and so even though it was heavier than Brunel's specifications, it would still have a relatively light axle load. The end result was a massive and very odd-looking machine made up of 3 segments. The front was essentially a 222 engine without the boiler, being fitted with a pair of driving wheels 10 feet in diameter and 6 tons in weight, and a pair of 16 by 20 inch cylinders. In order to operate the engine, the driver had to be positioned on this carriage. The middle was a 6-wheeled carriage that carried the boiler on 4-foot 6-inch unpowered wheels, the boiler itself having an impressive heating surface of 516 square feet, with the last wagon being the engine's tender. It was completed in 1838, delivered to the Great Western Railway in October that year, and named Hurricane. Hurricane's size made it a unique spectacle on the railway, with some saying, quote, "The engine formed a kind of procession when it passed." Its record-sized driving wheels too came with some impressive performance characteristics, with the engine supposedly averaging 84 miles an hour on a trip between Paddington and Taplow. Along with Hurricane came another engine, Thunderer. Similar in design to Hurricane, Thunderer used an 040 arrangement at the front, with smaller 6-foot driving wheels. Rather than power the driving wheels directly, the cylinders powered a separate wheel which drove the driving wheels via a gear, with the wheels having a gear ratio of 10 to 27. Both engines seemed to be impressive performers at first, but they both had a critical weakness, something I'll touch upon in a second. Only a few years later, in 1846, the Philadelphia and Reading Railroad's chief engineer, Mr. G.A. Nichols, was trying to find a way of running an engine on anthracite coal. The coal needed a large firebox in order to burn, and the boiler Nichols designed would be too big to fit on an engine without getting in the way of the driving wheels. To combat this, he mounted the boiler on a flatbed behind the locomotive, with a steam reservoir in place of the original engine's boiler. He named the engine Novelty, and while the boiler design proved to be somewhat functional, it was greatly let down by its poor drafting. To make matters worse, it also suffered from the same major issue that plagued both Hurricane and Thunderer: lack of adhesion. You see, while a locomotive boiler's primary job is to generate steam, its secondary function is to put additional weight on the driving wheels, pressing them into the rails to help them grip and provide better traction. Only a tiny amount of an engine's wheel touches the rail at one time. It's this lack of surface area that allows trains to travel so fast in the first place. But it also means that they struggle to grip the rails when starting or moving. By taking the boiler off the wheels, they no longer had that additional weight crucial for providing them with traction, meaning they lacked the strength to start or effectively move heavy trains. Even though Hurricane's driving wheels were 3 tons each, the extra weight needed to come from something pressing down on the wheels, not just from the wheels themselves. One can only imagine how tremendous the wheel slip must have been when starting a heavy train on a wet day. You could make the argument that to solve the problem, you could just add a water tank or blocks of scrap metal to provide the extra weight necessary, but that would only increase the overall weight of the entire locomotive, and is somewhat overcomplicating things when just mounting the boiler over the driving wheels is significantly more straightforward. As a result of their lack of traction, both Hurricane and Thunderer were taken out of service in December 1839. Hurricane's boiler was used to build an 060 goods engine named Bacchus, while its 10-foot driving wheels were used as part of a wagon to move a statue. Thunderer, meanwhile, was used as a stationary boiler, with the rest of the engine stripped for parts or scrapped. Over in the States, Novelty's poor steaming and abysmal adhesion also led to its downfall. It was rendered a failed experiment, and just like Hurricane and Thunderer, it was taken out of service about as quickly as it was put in. In the end, Hurricane, Thunderer, and Novelty turned out to be, well, novelties. While mounting the driving wheels in front of the boiler seemed like a good idea on paper, it just goes to show that the old saying about putting the cart before the horse still applies when it comes to engineering. Company secrets are always fun. Sometimes it's the secret recipe that's led the company to success, sometimes it's a secret to stop a scandal, and sometimes a secret is kept for no other reason than to prevent them from public embarrassment, such as the one the Midland Railway kept for 15 years. Cecil Paget, son of George Paget, chair of the Midland Railway, had a brilliant idea for a steam locomotive. To simplify, rather than using conventional cylinders, he proposed a design that utilised uniflow cylinders instead, with the main benefit of uniflow being that steam only flows in one direction in each side of the cylinder. This increases the thermal efficiency of the steam as it travels along a constant temperature gradient, whereas in other cylinders, the cooler, exhaust steam often flows across the hot end of the working cylinder, partially cooling the cylinder and by extension the injected steam, decreasing efficiency. It essentially works in a similar manner to a two-stroke engine, and in fact, it's possible to modify a two-stroke engine to run on steam and work the same as a uniflow one. Paget paid out of his own pocket to have the engine built at Derby Works, with the Midland Railway having to chip in after it was found the design was too expensive for him to build on his own. The end result was a 262 engine with outside cranks, 8 cylinders, and a total weight of 122.9 tons. It was completed in January of 1909 and testing soon began. It immediately suffered with its sleeve valves, as the body was made of cast iron and the liner that controlled the cutoff was made of bronze, both of which expand at different rates when heated, resulting in the bronze part seizing. To solve this, the pieces were resized, resulting in the valve gear working much better, but, quote, leaking like a sieve before it was properly warmed up. It was found the rotary valve gear absorbed 30% more power than the long D-slide valves commonly used, and the wheels and motion were balanced so well, the engine suffered from practically little to no hammer blow or vibration. Its firebox was also an interesting performer, primarily using fire bricks instead of a water wall like most other engines, helping simplify the building process. While it did suffer from bricks cracking and falling out, unlike other engines that used fire bricks, this design seemed to be very successful. For a few years, the Midland Railway tested it running trains between London and Manchester. It's believed that on one journey it may have reached a top speed of 82 miles an hour. However, there's little to no evidence actually confirming this. Its last run was in 1912. 1912 when it failed at Siston. The pistons had been working without steam, resulting in them cracking and getting stuck. It ended up blocking the main line for roughly 7 hours before the valve gear could be disconnected and be towed out of the way. The engine was soon put into storage while the company tried to figure out what to do with it. An interesting side note was Paget's relationship with the rest of the railway. Richard Dealey, the railway's locomotive superintendent, had a somewhat acrimonious relationship with Paget. Because Paget was the son of a chairman, he had many ideas he wanted to put in place, despite Dealey being his superior. As such, it was likely Dealey wasn't keen on further testing Paget's project that showed little improvement over conventional locomotive designs. On top of this, blocking a main line for 7 hours was not something the directors could easily forgive, likely making them view the engine as more trouble than it was worth. There's no concrete proof this is why the engine was sidelined, but it's still a fascinating point to consider in the engine's downfall. The engine remained in storage until 1918, when it was officially scrapped. Interestingly enough, Paget was serving in France at the time the orders were given to cut up the engine, with some speculating that management waited for Paget's proverbial back to be turned before they disposed of it. Again, hearsay, but a curious note nonetheless. What's most intriguing about this engine was how secret the Midland Railway kept it, as the general public knew next to nothing about it. Only one official photograph of it exists, and even then it was only released to the public after the Midland Railway became part of the LMS in 1923. Why they covered it up, nobody's really sure. Whatever you want to blame, bad design, awkward failures, or simply covering up a little corporate nepotism, Paget's engine remains a fascinating mystery to railway enthusiasts still to this day. Steam engines can be fueled with many different things. In the early days, some were powered by wood, many relied on coal, and in the later years of steam, a large number of engines even ran on liquid fuels like oil or gas. Over time, many engineers have tried to find alternate or more efficient fuels to run their engines on. One of these engineers was Oliver Bulleid, who had the revolutionary idea to try and fuel an engine with mud. For decades, Ireland and Irish railways experimented with burning turf, or as it's more widely known, peat. To simplify, peat is made up of moss, plants, and other wetland shrubbery that has built up over time and partially decayed into a mud-like state, essentially organic matter that's in the beginning stages of becoming a fossil fuel. It mostly forms around bogs or similar kinds of wetland and has many uses, but primarily, when dried out, can be burnt to produce a substantial amount of heat. It had been used for centuries as a means of cooking and domestic heating, so naturally, many engineers wanted to see if it was capable of powering a steam engine. Many tried, but given the abundance of coal and the fact peat didn't burn quite as hot as coal, peat-fired designs never really took off. It wasn't until the 1930s when Ireland took a renewed interest in turf-burning designs. Wartime coal shortages, combined with goals of rural development and energy security, led to a demand to increase turf production. Some railways had to use turf in place of coal when supplies ran low, and eventually alternatives to coal were being looked into. The CIE converted 93 engines to burn oil in 1946, but this project was quickly abandoned after coal supplies picked up again. Andrew Barclay built 3 narrow-gauge engines specifically designed to burn turf in 1949 for use in Ireland, but these only lasted 3 years before being withdrawn. In 1949, Oliver Bulleid retired from British Railways and was brought in as a consulting mechanical engineer for the CIE in Ireland before moving up to chief mechanical engineer. He helped the railway with the process of dieselisation. However, with diesel fuel still being relatively expensive and the advantages of diesel still being unproven, Bulleid felt it was worth exploring other options and took a keen interest in turf-burning designs. After several laboratory experiments using stationary boilers, he moved on to testing a full-sized engine running exclusively on turf in 1951. He took a former Great Southern and Western Railway Class K3 and had it rebuilt with a firebox fitted with air pipes, 2 Crosty-style feedwater heaters, preheating coils in the water tank, the chimney was set behind its tender, and turf would be fed into the firebox by an auger. After problems with steaming, the engine was fitted with a forced draft fan, which was mounted onto a wagon behind the tender and powered by a Leyland bus engine. With mixed results, the engine was eventually broken up in 1957. Armed with all the knowledge he needed, Bullied finally got to work on putting together his turf-burning engine. Wanting to make an engine with all the comforts of modern diesels, and with his leader design still fresh in his mind, he set to work. The end result was a tank engine fitted with a double-ended boiler, 2 cabs, feed water heaters, induction fans to improve airflow, and mechanical stokers, mounted on 2 sets of swiveling bogies. All the wheels were powered by a 2-cylinder steam engine and connected with a chain transmission. The CC1, as it was dubbed, was more comparable to a double Fairley engine in a square casing than a standard locomotive. It was shorter than Bullied's previous leader design, lighter, had fewer cylinders, and was balanced much better. Testing began in July of 1957 primarily between Dublin and Cork. It was found to handle well, capable of travelling comfortably at 70 miles an hour while maintaining a favourable noise level and burning turf at a moderate rate. However, despite its articulated design, it was found to handle poorly on tighter curves. Some problems the engine suffered with were easily amended, such as exhaust smoke and steam blocking the driver's view, necessitating smoke deflectors be fitted. The engine also supposedly caused several line-side fires, leading to spark arresters also being fitted. Some problems it suffered from, however, couldn't be so easily amended, such as its high water consumption as well as leakage of the chain drive's oil baths. A problem many of Bullied's designs suffered from. Another major drawback of the design was the positioning of its controls, as when operating from its number 1 end, it was fine, but when driving from its number 2 end, both the driver and the fireman were positioned on the same side of the engine, making it awkward to see ahead when they had to share the same space. Despite its shortcomings, CC1 proved that firing an engine on turf was entirely plausible, and that with a little more refinement, Ireland was more than capable of producing a fleet of turf-burning machines. John Click, an engineer that had been helping with the trial, designed a single-ended version of CC1, which would address many of the engine's issues. The idea was to have the engines primarily burn oil, but could easily be converted to burn turf in an emergency. Unfortunately, this design never came to fruition. CC1 continued testing, and was even reported to have hauled several freight trains around Dublin. However, when Bullied retired in 1958, CC1 was retired as well. Despite its success, with Ireland moving towards dieselisation, it was likely the railway didn't consider turf burning or other steam variations worth developing further if they were to be obsolete in just a few years' time. As such, Click's designs weren't pursued, and the CC1 project was abandoned. CC1 was officially withdrawn in 1963 and broken up in 1965. with its boiler being retained for stationary use while its chassis remained in Inchicore. A CIE executive later remarked that scrapping the engine was a pity, and that such an oddity deserved preservation. In the end then, the CC1 was just another tragic example of a good idea in the wrong place at the wrong time. The fact Bullied managed to pull off building an engine that could be fired on turf and still perform is quite an achievement, but given that the rest of the world was starting to move on from steam simply meant it got left behind. If the design came a few decades earlier, it may have completely changed Ireland's railways. But alas, the CC1 remains a reminder that it isn't always the idea that's bad. Sometimes it's just the timing. For over a century, steam was the most dominant form of motive power on railways around the world, but the invention of the internal combustion engine was starting to change the status quo. Diesel engines could theoretically produce the same amount of horsepower as a steam engine, but in the early days there came the issue of getting that power to the locomotive's wheels. Many different methods were tried, including mashing a steam locomotive and a diesel engine together. Nowadays, the most ideal way of utilising a diesel engine in a locomotive is with diesel-electric transmission, where, long story short, the engine powers a dynamo which generates electrical energy, which is then sent to the motors driving the engine's wheels. In the 1920s, however, when diesel engines were first emerging, the dynamos and electrical equipment needed to generate the power weren't quite compact enough to fit snugly in a locomotive, and were very difficult to build and maintain. As such, other forms of transmission were looked into. Mechanical drive isn't best suited for big locomotives, and hydraulic transmission was very rough around the edges, and so eventually the idea came about to simply try the same transmission as steam locomotives. To simplify, the way a steam engine works is high-pressure steam enters one end of a cylinder and is exhausted out of the other. This is then reversed, so steam enters the other side while being exhausted out of the opposite end, creating a backwards and forwards motion. The cylinder can then be connected to a wheel to rotate it, and boom, you have propulsion. Because the cylinder works with pressure, it's entirely possible to propel a steam engine using compressed air in place of steam, and that's exactly what Germany tried to do. In 1924, the Deutsche Reichsbahn ordered a diesel locomotive from Maschinenfabrik Esslingen to test on passenger services. The Class 78s had proven to be ideal express passenger tank engines, and so it was decided the new diesel locomotive would be based on them. After 3 years of development, a prototype engine was finally put together, essentially using the frames and motion of a Class 78, but fitted with an MAN 2-cylinder double-acting single-stage air compressor powered by a 6-cylinder LO6 VU4542 engine originally designed for use in U-boats. The compressed air would be sent to the 2 cylinders at the front of the engine, which powered the wheels in the same way steam from a boiler would, making it possibly the first diesel pneumatic locomotive in the world. Measuring in at 15.8 meters long, the 464 weighed 111 tons, had 1600mm driving wheels, 710 by 650mm cylinders, and a cab at either end. It was numbered V3201 and testing began in 1929 around Stuttgart, where it was found the locomotive was capable of reaching 80 km an hour while pulling a heavy train. Not only that, but it was capable of starting a 233-ton train on a grade of 1 in 40 faster than most other steam engines of a similar size. Further testing seemed to yield positive results, but despite the exceptional performance, it seems that it wasn't enough to justify how complex the machine was to operate and maintain. The compressor's cylinders needed cooling, and this was achieved by injecting minute amounts of heated water into them as they worked, water that was heated by the engine's exhaust to help make injection easier and to prevent buildup of scale in the system. This also, however, meant that steam could condense into water in the system, and bleed valves had to be installed to prevent any kind of water damage. In order to work properly, the air used to drive the wheels needed to not only be compressed, but heated to expand too. As such, once it was compressed, the air would also be warmed up using waste heat from the engine's exhaust before arriving in the driving cylinders. On top of that, compressing air produces a lot of heat, resulting in a significant amount of energy being wasted, making the process very inefficient, especially as you not only have to cool the air, but then also need to heat it again. Compare that to a steam locomotive that simply needs to heat the water in its boiler before sending it to the cylinders in order to achieve the same performance. Eventually being renumbered V120001, testing of the locomotive continued until 1933, and while it did perform well, its complex design made it costly to maintain, and despite the addition of radiators and water injection, the air compressor was prone to overheating. By the end of that year it was withdrawn, being scrapped sometime between 1933 and 1935. While not the technical achievement Deutsche Reichsbahn had hoped for, the experiment did pave the way for DRV 140001 and other diesel hydraulic locomotives. Italy also experimented with diesel pneumatic locomotives, but that's another story for another day. As technology improved, diesel-electric transmission eventually became the standard for diesel locomotives, with diesel pneumatic fading into obscurity. Diesel and steam locomotives are often viewed as chalk and cheese, one being the antithesis of the other, but the DRV 3201 is a unique example of two seeming opposites coming together and creating something amazing. It might not have been a perfect locomotive, but it certainly shows us that even things we normally view as incompatible still have the potential to work in harmony. The one thing I can't figure out, however, is since it's both diesel and pneumatic, would it have had a horn or a whistle? I think I'll leave that one up to the comments. As gorgeous and loved as steam locomotives are, many of them suffer from one big problem: visibility. The driver's cab being set at the rear end of the locomotive means that the driver's forward view is partially blocked by the boiler, making reading signals and watching out for obstructions much harder. Many attempts were made to reposition the cab to give the driver a better view, but this task came with a few complications. Hailing from Egypt, Mr. M. Henry Thuile grew up to become quite a keen engineer, working as an engineer at the port of Alexandria before moving to France and becoming a member of Société des Ingénieurs Civils in 1894. That same year, prominent engineer Gaston du Bousquet remarked how passenger trains should travel at 120 km an hour, and that the main reason they don't is because they can't. Struck by these words, Thuile started designing locomotives with the goal of producing an engine that was capable of hauling high-speed luxury passenger services. He founded his own company with the goal of running his own Orient Express-style services across Europe, but unlike the Orient, it'd be the same locomotive pulling the train the entire journey. He eventually produced a locomotive with limited success. Afterwards, he toyed with the idea of using 648 and 646 wheel arrangements and wanted to use massive 3-meter driving wheels in order to achieve his desired top speed. Eventually, he settled on a 446 wheel arrangement and came up with quite a unique machine. He took the plans to Schneider & Company, who put the engine together, and the final result was a 14-meter long behemoth. It was equipped with 4 2.5-meter driving wheels, a pair of 510 by 700mm cylinders, a Belpaire firebox with 2 firebox doors, Walschaerts valve gear, Westinghouse brakes, and a dynamo on the rear bogie used to generate electricity for both the engine and carriage lighting. Its two most unique features, however, were its forward-mounted cab and its unusually shaped boiler. Thuile wanted to give the driver the best possible view, and so positioned the driver's cab at the front. From this position, the driver had control of the engine's throttle, gearing, brakes, sanding gear, bleed valves, whistle, and the dynamo. To allow communication between the driver and fireman, an acoustic pipe and bell was fitted to both cabs. Meanwhile, in order to accommodate the massive driving wheels Thuile wanted, he needed to make the boiler smaller to fit between them, but a smaller boiler would mean less power. To solve this, he designed a sort of upside-down pear-shaped boiler, essentially being two boilers fused together and reinforced. Despite the inherent problems presented by non-round shaped boilers, it appears the design worked surprisingly well, capable of producing over 210 psi without issue. The tender too was massive, measuring in at just over 10 meters long on its own, capable of holding 7 tons of coal and 27.5 tons of water, further showing Thuile's ambition to make it a long-distance machine. Once completed in 1899, Thuile named the engine Trans International No. 1 and displayed it at the Paris exhibition in 1900, where many reporters both praised and panned its unusual appearance. He started testing his locomotive between Château and Troyes in May that year, the Chemin de Fer de l'État happy to trial the engine as it hadn't cost them a penny to build. During these trials, the engine managed to reach 117 km an hour while hauling a 180-ton train, and peaked at 80 km an hour while pulling a 200-ton train up a 1% gradient. As impressive as these speeds were for such an unusual engine, Thuile's design came with many drawbacks. To start with, its size made it very cumbersome to handle. Its length meant it couldn't handle curves with a radius tighter than 500 meters when going at speed, something that was quite common on the line it was tested on. And its weight didn't help either. On its own, the locomotive weighed just over 80 tons when fully loaded for service, the tender only adding an additional 50-ish tons to the mix. Its length and lumbering weight caused it to derail on multiple occasions, and its inability to make turns at speed resulted in crews having to slow down and lose time on a run. Not that its speed was impressive anyway. Despite his goal of wanting to make a 120 km/h machine, it's said that Thuile's engine refused to exceed 117 even in ideal conditions. Part of this is likely due to its wheel arrangement. Yes, the bigger wheels would help improve its speed, but with only 4 out of the 14 of the locomotive's wheels being powered, and despite the engine's immense weight, only 40% of that weight tops was being applied to the driving wheels, meaning that even if the engine had the power, it lacked the adhesion to apply it. Another flaw in the design was the forward cab for the driver. The main benefit of having the driver and fireman together is it not only makes communication and coordination between the two much easier, but also should one of them fall ill or become injured, then the other is capable of taking over until it's safe to stop. Even with a bell and acoustic pipe, separating the driver makes things unnecessarily hard, and often requires an additional driver be present to ensure the safety of the crew, meaning the railway needs to pay more staff to run one engine. And to be frank, the boiler obscuring the driver's view wasn't that big a deal, as most signals were arranged to be easy for drivers to see from their position anyway, and the fireman could look out the other side of the cab to help cover any blind spots. Perhaps one of the biggest drawbacks was its boiler. Though no issues were reported during the trials, the unusual shape meant it was not only more complex, and thus more costly to maintain, but also meant it was next to impossible to standardize should the design have been picked up by another railway. All for a boiler design that was slightly less efficient than a standard barrel shape. But most damning of all was simply the fact that Thuile's engine was being outperformed by many other contemporary designs which were lighter, faster, shorter, and much easier to run and maintain. It's claimed that Thuile's design was built to run on level tracks with little to no grades and shallow bends, but considering he envisioned it to run across the varying rails of Europe, its inability to traverse grades as small as 1% without losing a noticeable amount of performance said enough. The trials came to an abrupt end in mid-June after only 3 weeks of testing when Thuile died in an accident during a run. The official account given by the French National Railway Museum is that he was thrown from the footplate of the engine after it derailed. However, most other sources say that the engine didn't derail, and that he simply leaned too far out of the side of the cab to inspect the locomotive during the run, and his head was struck by a line-side post. Ironic, really, when one of the main selling points of the engine was better visibility. With its inventor dead and no signs of improved performance, the engine was quickly sent back to Schneider and put to one side. There it remained for 4 years before finally being scrapped in 1904, its tender surviving until 1946. What it was used for, I'm unsure. Cab-forward steam locomotives aren't a unique thing in the world of railways, and there have been some examples of the design working perfectly, but few may have been quite as unusual as Thuile's luxury engine. Even if the visibility wasn't the best, a rear-mounted cab was still a functional and semi-practical layout for steam locomotives, and all the other unusual changes he made to try and outperform the fine functioning contemporary designs, well, let it be a lesson that sometimes trying to fix what isn't broken might just cause you to lose your head. Subscribe for more.